introduced the contribution of the friction forces in geostrophic flow. So we started by considering this Prandtl hypothesis, where we have a solid bottom, then we have an interior, and then we have the boundary layer. Okay? So the existence of the boundary layer means that the Ekman number is order of 1, while in the interior we keep the Ekman number much smaller than 1. Okay? The fact that we have Ekman number order of 1 gives us the opportunity to keep the second derivative of the equation of motion, and so to add a new boundary condition, which is that the velocity at the solid bottom, u at zeta equal to 0, is equal to v at zeta equal to 0, which is equal to 0. While in the interior, we just consider, we started by the very easy case to consider just, let's say, u equal to u bar over 0, where u bar is the geostrophic component. Okay? So we found the equations. We have the equations u and v, u bar 1 minus e minus zeta d cosine z over d, and this is u bar e minus zd sine z over d, where d is 2 ni over f, which is what we call the Ekman layer. Okay, so it's the scale of the what we call bottom Ekman layer. Then we realize that if we go very close to 0, or we take z much smaller than d, so we are very close to the solid bottom, we have that u is order than v, which is u bar over multiplied by z over d. Okay, which is exactly the same function that we have for both u and v. And then, of course, when we go to infinite, so z is much larger than d, we have that u is exactly equal to u bar, and v is equal to 0. So the shape of the solutions has an exponential term, which gives us the switching off, the decreasing of the rho of the solid bottom. So the larger is z over d, the smaller, of course, will be this term. And then we have a trigonometrical dependence. The other thing that we can understand is that if we calculate the maximum of u, we say that the maximum, u max, is u at z equal to 340, which is 3 pi 4 d, which is 1.07 u bar. So there is a point, which is this one here, where we are, let's say, 3 pi means 9, more or less, so about twice time d. Okay, so 3 by 3 is 9, divided by 4, more or less 2. So at z, more or less twice d. So here, let's say, okay, already in interior, but not exactly too far from the boundary layer, we have that the velocity is slightly larger, so it's 7% larger than the geostrophic velocity, which was which was also depicted by this sort of bump that you have here, okay? So still we are close to the bottom. There is a point where we have a maximum value which is slightly larger than the value that we have in the interior. Another interesting property is that if we calculate what we call transport, so I will use the capital letters to define the transport. What is the transport? Transport is nothing more than the integral over dz over the entire depth, so from the bottom up to the infinite, so up to the interior, of v dz. Yes, okay. So I just integrate. It's some sort of average velocity. Okay. So is dimensionally speaking, capital V is square meter by second. And if we calculate this, it is u bar d over 2. So it's a constant, depends on the Ekman layer, but most important is different from 0. So the most important, one of the most important things that we can learn from the bottom Ekman layer is that even if this deviation that, as you have seen in the north hemisphere, is on the left with respect to the geostrophic motion. So we have the geostrophic motion in the interior, which is here. Okay, so every single point here is a value of z over d. Okay, so it's a dimensional. Since we are dealing with the cosine and sine, of course, it's much easier to use radians. And so if we have a deviation from the geostrophic flow, which is still, in any case, related to, you see, up to z over d larger than pi 2, so it's about 3/2. So always happens within the Ekman layer. Okay, everything, all the deviations happens within the Ekman layer. But still, even if it happens on a very short distance, because you remember that d is much smaller than h, okay, which h is the vertical scale of the height, we can have a transport which is not 0. So in any case, this flow is creating a transport. So if I integrate the transverse velocity over the entire flow, the entire water fluid column, I obtain an effect which is concrete and measurable over the entire fluid column.
Which is that V velocity from the first expression?
This, yes, exactly.
The second?
This one.
Oh, okay.
So you can just, it's easy, okay? So you can just integrate this and you will obtain this. By the way, if we do the same with the capital U, we will have the same value but with minus. Okay, so by integrating this one. Okay, so we can now extend a little bit the first.
Sir, can you take the Ekman transport again?
This one.
Yes. What does it mean?
So this is, you have the transport. So what is the average effect of the velocity field over the entire fluid column? So it's a sort of, it's mathematically speaking, is an integration, but you can consider this. If you consider like V over capital H, this is dimensionally is square meter second over meter, right? So it's meter per second. Okay, so V over H, so the transport divided by H, is the sort of average velocity. So this is nothing more than the same. Since h is constant, we have the meaning, that the physical meaning is related to the average something. In this case, is the transport. Okay, so it's the effect of the fluid, of the flow, over the entire fluid column, which is strange in some sense, because the idea is that, okay, our flow is strongly streamwise, is the maximum value is the geostrophic velocity is on the x direction, and we have only a small deviation in the transverse direction, but still this small deviation has an effect over the entire fluid column. Okay, so now we want to create to have a condition which is a little bit more general. So we allow to have both U bar and V bar in the interior flow. Keep this. And we will do exactly the same analysis. So we also consider, in the first case we had P, which was a constant. Now we have P, which is also dependent on time. So we allow very generalized non-uniform currents. So the equations are the same. So we will again have minus Fv equal to minus 1 rho 0 the xp, and Fu bar the yp. So this is the solution, the geostrophic solution. Okay. So you remember before we had this equal to 0, no? Now we just keep it. And of course, if we substitute, we will have the equation will take this form. So in the first case we didn't have this, we have also this one. Okay? Nothing very much different from before. What we obtain is that the solution will not just contain only U bar, but contain also V bar. So the solution we had before, we also have minus V bar E minus Z over D sine Z over D.
What are you seeking to do?
So I'm just allowing to the interior flow, to this geostrophic flow, to have also the velocity in the transverse direction. So generalizing a little bit more the simple case that we saw initially. And so the two solutions will be the same as before, but of course we will have V bar. Okay? So now we want again to calculate the transport.
Sine, is that sine? Sine over t.
This is sine Z over D, cosine Z over D. So you see that there is quite a lot of symmetry. So for those of you who are more mathematician, you can say that you can compose this solution by simply considering U bar, V bar, and cosine and sine. And you can have like sort of vectorial scalar product among two different matrices. Okay, D is always the same, doesn't change. So we can calculate U and V. So again, so why I'm leaving here? I did exactly the same before in the first case, but V bar was 0, okay? But this is the most general function of the transport, because I want to understand what is the transport only related to the non-geostrophic component. Okay? So I'm taking U, which is this one, and of course, if we are going to Z over D, Z much larger than D, of course, all this part here will go to 0, and we remain only with U bar. Okay? So the boundary conditions are always satisfied. Okay? Because this part goes to 0, this part goes to 0, this part goes to 0, and this part goes to 0. So we just remain with U bar and V bar, far from the boundary, and we are okay. So we want to understand what is the transport in the X and Y direction if we just consider the effect only due to the Ekman layer. So I'm just taking the velocity and I remove the geostrophic velocity. Okay? So just to understand what is the effect given by the fact that I have the Ekman layer. So, making the calculation, we obtain something which is similar to what we had before. So before we had d minus d half multiplied by u and d half multiplied by u. Okay? So we add these two. And now we can say, okay, that's very interesting. So we are having an effect due to the existence of the Ekman layer, which is basically depending on the geostrophic flow. So, sorry.
I missed the point there.
So we did the same as before.
Not about the calculation, but is the fluid flowing in the Y and the X direction, or what is?
Yes, we are having a X and Y direction in the interior and a X and Y direction in the Ekman layer.
So when Z is infinity,
When Z is infinity?
yeah, U will be 0. This from this expression.
No, when U will be equal to U bar.
Yeah. Okay.
Still, we have one here and one here. Okay? So all this part here, because this goes to 0, this goes to 0, this goes to 0, and this goes to 0, but we still keep this and this.
So the flow velocity is constant, that means?
The flow velocity is constant because we said that in the interior we don't have any possibility to, there is no change in time of our geostrophic flow. So the transport is basically related to the geostrophic flow. So we want to ask something. So you remember that on the F plane, how much was this? 0. So we remember that on the F plane, geostrophic flows are non-divergent. So I said, okay, is it the same for the transport? So if we are having a transport which is in the U and in the V, what is the divergence of the transport? So how the transport evolves, and let's say, which is the effect of the bottom Ekman layer over the transport. So this means nothing more than applying the X derivative and Y derivative to this. So we can write something like this. Okay? So from this I have the XU minus the XU bar plus the YV minus the YV bar. So I can put these two, I put a minus, and I have dx u bar plus dy v bar. Okay? So this part here goes to 0 because we know that is 0. So we just obtain du dx plus dv dy in this end. But if we apply, so this is practically the calculation of the divergence, because now is no longer the divergence of the geostrophic flow, because that is 0, but it is the divergence of the u and v, which is the whole flow. So don't forget this. U bar and v bar are like parameter of our problem. U and v are the solution of our problem. So now we can apply this, rather than calculating all of this, we can just apply this to this function here. So we have minus d half, and we have d u bar dx plus dv bar dx minus u bar dy plus d v bar dy. So again we have du bar dx and dv bar dy, which still is the divergence in the geostrophic flow. And what we obtain is dv dx minus du dy. Can you recognize what is that?
Yes,
dv dx minus du dy.
what is it?
Is the vorticity, is what we call zeta. And I will put a bar because this is the vorticity in the geostrophic flow. So I'm saying the geostrophic flow is meandering, is moving with all its characteristics, two-dimensional, no divergence, and so on. Like the picture that we saw last time on the United States. But this this doesn't have any problem with having a vorticity. So we are saying that there is a divergence. So this is positive when we have negative vorticity. And we will have a convergence when this will be. So we can have two cases. In this case here, we have divergence of the transport, Ekman transport, and divergence means vorticity negative. Vorticity negative means anticyclonic motion. Okay?
Divergence means vorticity.
Sorry?
Divergence means vorticity positive or negative?
This is positive. This must be
Negative.
negative because we have minus here. And of course, the contrary. So there is still something because as you can see here, there is a vertical velocity. Because we said that we cannot, if we have this in our geostrophic flow, we know also that v bar, which is the vertical velocity in the geostrophic flow, shouldn't change in z. We said at the beginning that if we have Ekman much smaller than 1, we do not consider any kind of boundary layer. We said that if vertical velocity is 0, here should be 0 on the entire. But now we have a boundary layer. So the boundary layer creates, like the velocity u and v, also the vertical velocity is going to decrease in a very short layer with respect to the interior one. So we can actually calculate this, but it is exactly this one. Because if we take this, so the ZW is equal to minus the XU plus the YV. And we integrate again in Z. So this term here is exactly this one, apart from a minus. So it's equal to d2 over the vorticity. And this is W at infinite minus W at 0. Right? So W at infinite is simply W bar. Is the W is the vertical velocity in the interior, in the geostrophic. W at 0 is 0. So we have a vertical velocity. So the vertical velocity in the interior, which is called Ekman pumping. Someone also use suction. It depends on the sign of the velocity. So it means that the vertical velocity has the same sign of the vorticity. So in this case, we have here vorticity, which is negative, and vertical velocity, which is negative, which close the mass conservation. So if we have an interior flow, which is geostrophic, which is in the ocean, for example, or in the atmosphere, has a vorticity which is non-zero, the presence of this vorticity will give rise to a convergence or divergence of the transport, which will push out or make converge the flow, and so have a vertical velocity from the top to the bottom, or from the bottom to the top. Of course, you can also represent this by using the pressure, because never forget that U bar, so it was like, is minus 1F rho 0 YP, and V bar is 1 rho 0F dXP. So if you put together these two expressions, the solution of the geostrophy here, you will have something which is proportional to the Laplacian of the pressure field, which doesn't say much more about the system, just the fact that we can have something which is like this, or something which is like this. So this is the pressure field. So in this case, we will have, this will be positive, I think, and in this case, it is negative. I think maybe it's the contrary.
Sure.
No, it's contrary. Yes, because when we have this one, we will have,
Local instability.
sorry, local instability. Well, we just have that here, in this point here, the pressure is larger than here. So we have a high pressure. Indeed, this sign here is related to a vertical velocity, which is towards the bottom. And this is the other case. Okay? So this is quite very well applicable to atmosphere. Okay, so we can compute the Ekman layer. I won't say too much about that, but just as a curiosity. So
Where do you substitute this one to get Laplacian?
here. So if you have dv dx, so dv bar dx is equals to d dx, and v is 1 rho 0 f dxp. So you have second derivative of b. Okay? Then you have a minus, which counteracts this minus here, and then you have this. Mathematician or physician?
No.
These are very, very simple. Okay, so just to create a little bit of confusion, no, I'm joking, but if we don't have a flat bottom, but we have something which is like this, so we have a topography, okay? The solutions are exactly the same as we had before. So if this is again b, which is a function of x and y, we will have all the same thing as before, just that difference is instead of having z, we will have z minus b. Okay? Nothing more. So all the you will have not e minus z over d, but we will have e minus z minus b over d. And of course, sine or cosine of z over d will become sine and cosine of z minus b over d. Okay? And we can still do the same analysis and calculate the vertical velocity. So the Ekman pumping in this case, we will obtain still the same W equal to B half multiplied by vorticity, plus we will obtain term here, which is the same term that we found, so the scalar product between the velocity and the gradient of the topography, okay? Which is the same that we found, if you remember, a couple of lectures ago, when we were analyzing the geostrophic flow over the complex terrain. Okay, so that I won't ask you this at the exam, okay? So I will. You can read it, but it's not so interesting. One thing much more interesting is if we move to everything fine so far? This means yes. I had a very good friend, but he was from India, and at the beginning he said, "How are you? Are you okay?" Also in Bulgaria they do like this. In Bulgaria they do like, this is yes and this is no.
Just opposite.
Completely. At least you are, let's say, something I can understand a little bit. Okay, now we move to the other case of Ekman layer, which is the surface Ekman layer. So the surface Ekman layer is the one which actually gave the, let's say, the popularity to Ekman. Because as I told you last time, Ekman wrote his PhD thesis on this problem. Because his professor, Nansen, used to travel over the Arctic Ocean and observe, take a lot of, have you ever been in Oslo, in Norway? No. Okay, if you have the opportunity to go to Oslo, there is a museum, which is called the Fram Museum. Fram is the name of the ship of Nansen, and that was a ship which was built to travel in the ice pack. So they were traveling, they waited that the ice pack was formed, and then the pack was formed, the ship was blocked by the ice, and they were floating in the ship with the current. And then they make a lot of experiment and obviously living there for all the winter. So one of the things that Nansen observed was that the iceberg were going to drift on a certain angle, say 20 degrees, 30 degrees, let's say something like 10 degrees, depends, on the right with respect to the wind. So I said, why? And so he gave this problem to his pupil Ekman. And Ekman resolved the problem by creating this model, which today appears quite simple, but at that time was absolutely not. So we have still the same equations. So I can again put E here. There is no. That. So now we have a situation which is reversed with respect to the previous one. So before we have the interior and then the bottom, and the Ekman layer was close to the bottom. But now we have the interior which is in the bottom, and the Ekman layer which is the interface between the interior and the sea surface. So there is again a discontinuity. Before we had this discontinuity between the fluid and the land, or let's say the atmosphere and the land, or the ocean and the sea bottom. Now we have the discontinuity, in this case, which is the most easy to understand, is in the ocean. So we have the discontinuity between the atmosphere on the top and the ocean above the surface, the sea surface. So we put Z equal to 0 here. So Z is always going from the bottom to the top. So now we will have to consider something which goes from minus infinite to 0. Okay? So before we were integrating between 0 and infinite. Now between minus infinite and 0. Actually, this can be also applied to the atmosphere if you consider this not like the sea surface, but like any kind of discontinuity, for example, the one that you have at the end of the troposphere, okay, when you have a strong discontinuity in the thermal field. Okay, so what is the difference between the bottom Ekman layer, according to you? So the equations are the same. So you remember, when we start to considering the second derivative, we need to specify what? The boundary condition. So the boundary condition are different. So we can say that when Z goes to minus infinite, U will be equal to 2.
You know,
We are here.
U bar.
U bar and V will be equal to V bar. When Z goes to 0, it's not 0. Look. So now you can also use intuitively. So we have the wind stress, and it's like a layer. So the wind stress is acting on the sea surface, moving the first layer of the surface at the same velocity of the wind, or let's say same order. And then all the other will progressively feel less and less the wind stress. Of course, if I don't have wind, I won't have any kind of change in the vertical. Okay, but since I can always consider that the wind is blowing over the sea, I have this kind of let's say vertical development of the velocity. So at Z equal to 0, so we have to express the link between the velocity field and the wind. So we have that rho 0 so we have to consider the wind stress. So you remember that when we started to analyze the equations of the fluid dynamics, we had the expression tau dj, right? So the stress tension. And the stress tension was mu du di uj plus dj ui. Okay, so now we are in a very symmetric situation because we just consider the z direction in this case. So u mu is rho 0 nu. This is the kinematic viscosity and this is the dynamic viscosity. No, contrary, this is the dynamic viscosity, this is the kinematic viscosity. And if we express tau xz, so tau xz is the stress over the x direction which transport the shear in the vertical. So will be rho 0 nu, so the xw plus the zu. So w doesn't exist, let's say, there is no change in this case of w with respect to x, so we cannot neglect. And so we just maintain the term dzu. So dzu is nothing more than the shear. Okay? So it's the vertical shear of the velocity, which is exactly this one, is the fact that the action of the wind stress is to create a shear, a vertical shear in the flow velocity, flow horizontal velocity. So rho 0 ni du dz equal to tau x and rho 0 nu dv dz equal to tau y. So if we are, let's say, on the top.
Why didn't you put the z?
Sorry?
The tau xy is not tau xz.
Tau, oh well, we can, you're right, we can write tau xz and tau yz, yes. But since we have only the z direction as the as the direction where we have the shear, we can safely, but it's correct, I mean, it's a good observation. In general, it is this one. Of course, if you calculate all the other, for example, tau xy, which is rho 0 nu the xu plus the yv. So, the xu, yes. So, this actually is a form of the divergence, which is not zero, okay? This is just exactly what is the shear, if there is a shear in the x, in u, or in the y, in v, okay? But what we are interested now is only the effect in the vertical. So I was saying that if we have like tau, which is like this, here we have tau x and tau x. Okay? So this actually is the wind field, wind or wind stress. Okay? So there is a small differences between wind. Wind, of course, is a velocity. The stress is a pressure. Okay? If you calculate the unit of measure. Okay, good. So the boundary conditions are a little bit more complicated. What happened is that we don't see how to find the solution, but we can see how are the solution. So u and v. So both will be U bar and V bar. So we will have that the solution will still keep the geostrophic component, and then we will have another component which has so we have a constant here, which is not exactly a constant, because depends on F. F is the Coriolis parameter. So the more I'm going towards the equator, the stronger will be this one. Then it's depending on D. So the shorter,
But the stronger would be which one?
sorry,
And the stronger would be which one? Is it the whole time or the Coriolis force?
I didn't understand,
I
sorry.
mean, you said the more you go towards the equator,
Yes.
the stronger would be.
F.
F.
So the F, if I go to the equator, F goes to 0, right? Because it's sinus. So if I go to 0, this will become much larger. So the effect of this quantity here, of this component, will be much larger when we are going to the equator. That's why this solution here is extremely important when you are calculating the equatorial dynamics. And then, of course, we have a variation of an exponential variation. So z now, don't forget that we are considering negative z. So when z goes to minus infinite, of course, all this term goes to 0. And we remain only with the geostrophy. So how is inside? Tau x cosine zd minus pi 4 minus tau y sin zd minus pi 4, and then tau x sine z over d minus pi 4 plus tau y cosine okay, so this is the solution of the surface Ekman layer. So this is the product of the thesis of Ekman. And this solution can tell us a lot of things. So the first thing is what we said before. So if we go to the equator, this component here, which is called wind driven. Why wind driven? Because if our wind is 0, there is it's 0. While in the bottom layer, the component, because you can have the same equation, the same solution, let's say, the similar solution in the bottom layer, like U equal to U bar plus something, V equal to V bar plus something. Well, the something here for the surface Ekman layer is related to the tau. So if wind is 0, there is no wind-driven component. In the previous case, if you remember, we have something which was similar because we have not tau x, but U bar and V bar. So the bottom Ekman layer exists everywhere and always, because it's just because of the existence of the geostrophic interior. The surface Ekman layer practically exists only because of the wind. And is stronger when we go to the equator, and the smallest is D, so the smallest is the Ekman depth, the larger is the wind-driven component. So we can do, again, the same analysis and calculate our transport. So U, capital U, and capital V. So now we are integrating between minus infinite and 0. And again, U minus U bar dz, V minus V bar dz. So after some calculation, we will obtain 1 rho 0 f tau y minus 1 rho 0 f tau x. So before we said that the transport in the fluid column, which we call Ekman transport, was related to U bar and V bar, no? So only to the geostrophic flow. Now it is related only to tau x and tau y. So if we have this expression here, no? So we have tau x, which is this one, and tau y, which is this one. So where is the vector u, the vector of transport?
I think in that direction.
This one? Okay, so Prakash is here. Other braves? The brave will be the one. Come on. So U is proportional to Ty. V is proportional to minus Tx. So let's consider this like 1. Okay? So U is equal to Ty. So Ty, this is U. And this is V, which is minus Tx. Minus. So Prakash is okay in the symmetric word. You were okay. Oh, no, you were brave, so I like the brave. Okay, so the transport is exactly at 90 degrees with respect to the tau, to the wind drift. Okay, to the wind stress. So this is the wind stress. And the transport is exactly at 90 degrees. So indeed, if we calculate the scalar product, we will have Ty, so we can put this, and we have Ty, Tx, this by this, and minus Tx, Ty, which is 0. Okay? So the transport in the Ekman layer is at 90 degrees in the northern hemisphere, because otherwise we have everything inverted, with respect to the wind stress. So Ekman says, you see, Professor Nansen, that's why your iceberg were drifting on the right with respect to the wind. Why? Because if this is the sea, you know that the iceberg, the tips is about 10% or something, or the entire volume of the iceberg. So the iceberg were actually within, probably, and even a little bit more, but strongly inside the Ekman layer. So the transport of the Ekman layer, the fact that we are putting all the velocity in our system, over the mass of the iceberg, was giving as a total effect a drifting on the right of the with respect to the wind. So we can calculate also here.
You said the Ekman layer exists everywhere in the ocean, right?
Mm-hmm.
And then assuming you are being given the data of all the parameters involved, and then you are asked to determine where exactly the Ekman layer is. What single parameter are you going to use?
Single parameter for what?
Yeah, I mean, how will you identify that this is the Ekman layer?
Oh yes, well, I can always calculate. So in any case, I can calculate this and put in, for example, the eddy viscosity. You remember, 10 to the minus 2 square meter per second. And this depends on the latitude. And we said last time that this is about 10 meters. Okay? Of course, it can be 20, 50, depends. Because this is a very rough estimate. But still, this is something that this function, this expression of the Ekman layer, we found it in the solution for the bottom Ekman layer, but still it holds also for the surface Ekman layer. Okay? So this way to estimate the Ekman layer, it's a model, okay? So Ekman layer, Ekman transport is all a model, is analytical. So of course we will see that this is something which does not exist in nature. But it's a good approximation to understand how things are going. For example, like this.
So, I'm not getting well how you interpret the.
So, this is the vector of the wind stress, okay? Tau x and tau y. Okay? So we calculated the transport in the x direction and the transport in the v direction by still using the same formula as before. What we obtained after some calculation, we obtained that u is equal to 1 rho 0 f tau y, and v is the same, but with minus and tau x. So if we highlight here the two components, tau x and tau y, and we consider just for example, that is not, this is just a very, very rough approximation, but if this is 0, this is 1 and this is 1, we have that u is proportional to ty and v is proportional to x. So these are just numbers, it's a parameter, so it can be larger or smaller. Still, in any case, u will be like ty, so ty is this. So the same value of ty that here is positive, we will have in u, okay? And v is proportional to minus tx. So if this is tx, we can consider this as v. So if this is u and this is v, we obtain that the transport, the vector transport u and v is 90 degrees with respect to the wind stress. Okay? And this is a very, let's say, easy representation, but we can calculate it a little bit more mathematically, and we can do the scalar product, which gives you that the scalar product is equal to 0. And when two vectors have a scalar product equal to 0, means that they are orthogonal one to each other. Okay?
But v is minus tau x.
Sorry?
I don't see how v, which is equal to minus tau x, how you
V is equal to minus
tau x.
tau x. Yes. So tau x is this one. So if this 10, this will be minus 10. So it won't be plus 10.
But tau x
Yes, this one.
minus tau x.
Yes, but I'm creating the value of over v. So I am on this axis. So think that tau is 10, 20. Okay? U will be 1 over rho 0 f. So tau I 20 minus 10. Now it's clear, no? Bling. Okay. All right. Okay, so now we want to still, I can delete this. So we want now to calculate another important value, which is the value of u at z equal to 0, which is u z equal to 0, v z equal to 0. So, if we want to calculate the velocity at the surface, we just have to take the solution of the problem and put z equal to 0. Easy, no? So, this will be 1. And here we will have all cosine and sine of minus pi 4. So there will be something with the root of 2 divided by 2. So if, again, we make all the passages one by one, what we obtain is this will be proportional to tau x plus tau y and minus tau x plus tau y. So actually, since now they are, tau x and tau y are present in both of the two components, we can, of course, find again the angle. So I know that the angle between two vectors will be, so if I have vector A and vector B, and this is the angle, so I know that alpha is equal to the magnitude of this two vector divided by, contrary. So it's the scalar product divided by their magnitude. Okay? So if we apply the same formula to u and tau, what we will obtain is that alpha is equal to 45 degrees. So
Cos alpha.
sorry?
Cos alpha.
So this is right. So we have to calculate the arc cosine of this. So at the end, what we obtain is a picture like this, where we have the wind stress blowing this direction, the surface current, which is at 45 degrees with respect to the wind, and the Ekman transport, which is at 90 degrees with respect to the wind, always at the northern hemisphere. Okay? And again, as in for the bottom Ekman layer, we have that the surface current will veer, will turn, in this case, on the right with respect to the wind, and create this Ekman spiral, exactly like we said at for the bottom Ekman layer. So the wind is actually blowing on the surface, creating a surface current which is 45 degrees. So if Professor Ekman, he was observing the iceberg drifting at not 90 degrees, but let's say ideally at 90 degrees, but if he put a drifter just feeling only the surface current, he should have seen that the drift will go 45 degrees with respect to the wind. Okay? So the iceberg, which feel the whole transport over the Ekman layer, will float at 90 degrees. The drifter only feeling the surface current at 45 degrees. So again, we can calculate the divergence of the transport, because this is very important. So before we found the divergence of the transport is dependent on the vertical velocity in the geostrophic interior. So we wonder if something similar we can have also here. So again, du capital over dx plus dv capital over dy, which is equal minus 0 du dx plus dv dy dz. So u was equal to 1 rho 0 f tau y, and v minus so if I apply directly this to this, what I obtain dx tau y minus dy tau x. What is?
0.
Not 0. Dx tau y minus dy tau x.
Z component of tau.
Z component of the vorticity. So we will call it and this is called the curl of the wind stress or wind stress curve, whatever. Wow. So we are having divergence. So when this is positive, we will have a curve positive. When this is negative, convergence, we will have negative. But what does it mean, positive and negative curve?
Rotation.
Sorry?
Positive means rotation along the direction of z.
Exactly.
It's opposite to the z.
Exactly. So we can have a shear on the horizontal of the wind. So ocean and atmosphere. Here we are having convergence in the Ekman layer, and so this is negative, and so we are having the curl which is negative. So we have anticyclonic motion. Opposite, divergence, and cyclonic motion. Okay? And of course, you can see the small arrow here, because from here we can calculate minus using still our continuity equation. Okay? So this will be minus W in 0 minus W in minus infinite. So this is 0. Okay, we have a discontinuity, and this is W bar. So we have that the sign is conserved when we have the curl positive. So curl positive means cyclonic motion. Curl positive means divergence. We have positive vertical velocity, and the contrary for this. Okay. Of course, also here you can no, you cannot do nothing with the pressure here. Yeah. So this mechanism, which is still called Ekman pumping, and in particular, this is called upwelling, and this is called downwelling. Okay? So upwelling is extremely important if you work with biogeochemistry, if you work with biology in the ocean. Because this thing here, so the effect of the wind, this is the most efficient mechanism that exists on our Earth to move actually over the vertical, the water, which is extremely difficult. Because think about how to create a motion which is vertical in something, in a fluid, which is typically stratified. We will see how much energy you need to create this kind of motion. So this kind of motion is strategic to have what we call the production. So this is a map from satellite where you have the actually the ocean color. Okay, so this is the radiation, the visible radiation that satellite measure from the top. And when you see blue, it means, let's say, poor water, so you don't have chlorophyll, okay? It's because chlorophyll react and has a visible reaction to the light. So it emits in the visible spectrum. So if it is blue, it means low chlorophyll. If it is red, yellow, it means high chlorophyll. So you can see that there is high chlorophyll, for example, over this, the western coast of the western part of the Adriatic here, because we have the Po River. Po River is the largest river in the Mediterranean, apart from the Nile. Close to the Nile, we also have a lot of production in this area because it's very low-level area, and then in the Black Sea. So why in this area we have upwelling? Because here we have we have productivity. Because here we have productivity close to the river. We have nutrients. Okay, so we have chemical elements which goes within the ocean and becomes practically the food for the phytoplankton. Phytoplankton eat nutrients, eat chemicals, nitrate, phosphate, and so on. There is a growth of phytoplankton, then a lot of phytoplankton. Zooplankton eat phytoplankton, small fishes eat zooplankton, and big fishes eat small fishes, and so on. And we eat small fishes and big fishes. But here, so here, it's true that we have a big river, but this production here is due to upwelling, because here we have a very strong production related to the Ekman pumping, because here we have a very strong wind which comes from the north and create, like this is the land, this is the wind, and here, since here wind is smaller, we have things like this, okay? So when we have the shear which has this direction, so here we will have upwelling, okay? Actually, this is the picture of a model. So again, you can see the same effect by in the northwestern Mediterranean.
What is the role of temperature in upwelling?
Sorry?
The role of temperature in upwelling.
The role of temperature. So the role of temperature is that usually what you have here is a stratified condition. So you have higher temperature here and lower temperature here. So when you have upwelling, what happens is that you have colder temperature which goes up. So you have a sort of mixing, and we will see, because now don't forget that we are still considering one of our hypotheses is rho equal to 0, so it's everything homogeneous. But still, this is a very good question. What happens is that we can move from a situation where we have low temperature here and high temperature here. And if you have this sort of mixing which is driven by the wind, what happens is this one. So you will have part of water that will go up, and other part of water, because of conservation, will go down. So there will be convection. And convection gives mixing. We will see it tomorrow, I think. No, tomorrow no, Friday, I hope. Okay, so very few words on what happened when we move to real cases. So in the real cases, of course, the Ekman models doesn't work properly, of course. So we need a lot of the hypotheses that we took don't hold. But this was one of the cases where the observation actually matched the theory. So this was a comparison between observed currents below a drifting ice flow, which practically is this one. So it's practically correspond to the surface current, and theoretical prediction based on eddy viscosity 2.4 10 to the minus 3. So it's a little bit smaller than the one we used. So we have the wind here, the surface current here, the geostrophic current here, that you can calculate geostrophic current by the satellite, you remember, by using the dynamic height. And so this is the actual Ekman spiral. So the theory is the dashed one, the observation is the solid one. So it was pretty good example of one of the few cases when you have theory that actually explain the reality. Because what we have much frequently is something like this. So this is observation in atmosphere. So this is U minus UG, so is U minus U bar for us. G is the geostrophic flow. And you can see here the vector is 14 degrees. So it's quite far from our 45 degrees. Why? Because in real cases, we have this situation here. So we have stratification. And stratification means that we cannot longer hold to the approximation of homogeneous flow, but the density is function of the vector. And when is this? And we have different layers in equilibrium with the density ρ1, ρ2, ρ3, which is larger than ρ2, which is larger than ρ1. So of course, the fluid adjusts itself according to gravity. So the lighter fluid stays on the top, the heavier fluid stays on the bottom. So this situation here, which is different from the hypothesis that we considered for the Ekman layer, actually create a sort of blocking, or let's say hindering of the vertical motion. So upwelling and downwelling are much more, let's say, much smaller. The other interesting thing is that we have turbulence. So we saw in few lectures before that the Reynolds number for GFD is much smaller than one, much larger than one. So GFD flows are turbulent flows. So, and of course, considering Ni as a constant is something that doesn't work. So the first model is to take at least a dependency in Z of the eddy viscosity. And if you do this, of course, all the Ekman model will become much more difficult. In any case, people, there was some example in literature of people who actually solved the Ekman layer with the specific form of the eddy viscosity. And what happened is that the angle actually between the wind stress and the surface current is smaller than 45 degrees, actually between 5 or 20 degrees. And the other thing that we can say is that the Ekman depth D, which we found equal to 2 over F, we can rewrite this by considering that the eddy viscosity, which has scales like square meter over second, so can be represented like a velocity, which is called u star, multiplied by a scale, by a length. Okay, so meters per second multiplied by meters. So the eddy viscosity can scale like a velocity, u star, multiplied by d. So d is the length of the Ekman layer. And what is u star? So u star is what is called the friction velocity, and is related to the wind stress. By this formula. So the friction velocity is related to the wind stress, which is this major player of the surface Ekman layer, divided by the density. So if we use this in the equation for the Ekman depth, it will scale with, we can leave the factor 2. So Ni will be u star multiplied by d over f. And so if we solve this by d, so we elevate to the second, we will have that. D actually scales like the friction velocity, oops, sorry, divided by f. And you will see that there is a proportional number, which is 0.4, which gives you the value of the Ekman depth in the, let's say, most real cases. Okay? So in the most real cases, what I use is not just the value of the eddy viscosity, but the value of the friction velocity, which is directly related to the wind stress, which is something much more easier to calculate. Because I know the wind stress by observation, I know the density, so I can calculate the friction velocity, I know F, so I can estimate D. Okay? Good. Okay, I have still few minutes to start the last argument, which does not consider stratification, which actually is the last approximation that we have on our shallow water model. So the shallow water model was the reference that we considered so far. So we avoided all this term, considered this, okay, with P, and added the friction and calculate the Ekman layer. Consider only these two, and we have the balance between Coriolis and pressure gradient, and we have the geostrophy. Consider all this, and we have the barotropic flow. Now, there is one still, so we avoided these three terms, then we added the friction here. We can still do something, so we can try to linearize these equations in order to say if there is one more simple solution to this model. So if we want to linearize, it means that we want to keep only the linear terms. Okay? Keeping the linear terms means that the system is easier to be solved. So which are the linear terms here? The first one is linear?
No.
Yes or no? No, no, no. Everyone say no?
Yes.
It's linear.
This?
No, it's
Not
linear.
linear.
This is not linear in velocity. U square, V square. This is linear?
Yes.
This is linear? Okay. So we just have to avoid this term here. So this is the idea, okay? So what we are going to consider is waves. So why waves? Because we said the Rossby temporal number, which is 1 over omega t, is order of 1. So we can consider it, okay? We can keep it. The Rossby number, u over omega L, is much smaller than 1. So if we take this and this, it means that the advection terms are much smaller than the local derivative and, of course, of the Coriolis. We still keep Ekman much smaller than 1. So for some reason, we have solved everything concerning Ekman order than 1. And again, we consider the homogeneous flow. So what means that Rossby is much smaller than 1? So it means that the velocities that we are considering are actually smaller with respect to the rotation rate and the length where they occur. While the time scale that we are considering are order of the rotation time scales. So with respect to this, we can consider this as slow field evolving relatively fast. So we have slow velocities of the fluid, but fast evolution. So we can say that these are phenomena which don't travel very fast, but change very fast. So if there is a parcel, this parcel possibly will move here, 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 or here, but the scale of velocity here will be much smaller than the scale omega L. So we can consider another velocity scale, which we will call capital C, which is L over T. So L over T is the length where the signal, this, let's say, information, we still have to understand what is, the information is traveling, divided by the time scale. So L over T, so is 1 over T is like omega. So it means that L over T is like L omega, right? But L omega is much more larger than u. So this scale of velocity, we call it celerity. Celerity, not celebrity, but celerity. It comes from the Latin and is the velocity of the signal. Why signal? Because we are having actually phenomena which are waves, because waves, you have that the information or the energy travels at this velocity, but the matter actually has a velocity u scale which is much smaller than this one. Okay? So think about a stone in a pond. Okay? If you throw a stone in a pond, you will see that you will create very fast velocity very fast waves. But if you measure the actual distance of each parcel within the pond, you will see that it will oscillate a little bit, maybe a little bit this, but not so much. Okay? So this is exactly this is exactly the kind of phenomenon that we want to find. So the barotropic waves are waves supported by inviscid because we have Ekman much smaller than 1, so we are far from a boundary layer. Homogeneous fluid in rotation, which is one of the possible simplification of the primitive equation in order to realize. So the Colonis terms are linear, it's okay. The advection terms are non-linear, so we have to simplify. And the local time rate of velocity change is linear, so we don't have to simplify. So we have to consider slow flow fields under rotation that evolve relatively fast, or rapidly moving disturbance that do not require large velocities, which means that information or energy might travel faster than the material particles themselves. So the field, okay? So next time, tomorrow, we will see the equations of the barotropic fields, and we will see some examples of barotropic fields that are existing in GFD.